All right, here's a brief introduction to repeated measures ANOVA. The learning objectives for this section are these: identifying when to use a one-way ANOVA versus a repeated measures ANOVA, and then interpreting the Excel output from an ANOVA two-factor without replication. So that's the title of the actual function that you'll use in Excel to do this type of ANOVA. You may remember that we discussed a couple of flavors of t-tests previously, where you have a one sample t-test, you have a two sample t-test with related samples, two related sample t-test, or matched pairs t-test, hence the pun here. And the difference between those two is whether you had data that was paired, if your two samples were paired and dependent on each other, or if they were independent. And some examples of matched pairs data would be things like before and after measurements, like before and after some treatment, where two measurements were taken on the same subject. Also, if you have data that just comes in pairs, like husband and wife, or two identical twins. If you can imagine your data in columns in an Excel sheet, if it's paired data, you don't want to take just one of those columns and shuffle up the order, because then you're not going to know which data pairs up with which, and that should cause you to freak out. If it doesn't cause you to freak out, if they're just totally separate groups and they're not paired up row by row, then you're dealing with independent samples. So you use an independent samples t-test, and there are two flavors of that. A repeated measures ANOVA is basically a match pairs t-test, but when you've got more than two means. So it's previously the other ANOVAs that we've talked about, a factorial ANOVA and the one-way ANOVA, are dealing with independent groups. Here you have typically one group, or at least for this type of analysis that we'll talk about today, you've got one group but multiple measurements on each individual. Okay, and it would also apply if you have groups that come in triplets, data that comes in triplets or quadruplets. So it's when you've got more than two means, then you want to use this repeated measures ANOVA. But same principle applies if you've got related samples where you don't want to shuffle up the order of just one column, then you want to use a repeated measures ANOVA instead of a one-way or a factorial. Now, in terms of making the decision when to use this versus another one, it's best to kind of think of this, at least the repeated measures ANOVA that we'll talk about here, as being most similar to a one-way ANOVA, where one way you have independent samples, and with the repeated measures you have related samples. Okay, the factorial ANOVA, you can have factorial ANOVA with repeated measures. You could probably imagine some scenarios in which you'd have a factorial ANOVA, a factorial design where you've got two independent variables, but you still have repeated measures. For example, if you had two groups like controls and patients with bipolar disorder, and then you track them each for, you did three measurements on each individual, you'd have two independent variables there. One would be a repeated measures variable, a between subjects variable is what it would be called, or no, excuse me, within subjects, and the other would be between subjects. We won't get into that one, but that's a commonly encountered factorial design where you have some factors that are between subjects and some are within. But for this course, we'll only cover where you've got two factors and they're independent groups. And you've got independent groups, but they're organized and characterized by different levels of two independent variables. Okay, so hopefully the factorial designs are they're easier to spot, and it's easy to see that they're different from these. And hopefully when I provide this example, you'll see that it doesn't really look like a factorial design where you'd have, you could kind of organize it in a table in that way. Okay, so here's an example of some data that you would measure with a repeated measures ANOVA. Now, this is still called a two-way ANOVA. For example, in Excel, you'll still call this a two-way ANOVA. But it kind of looks more like just a one-way ANOVA, except you have repeated measurements taken on each subject. Okay, so here are 25 subjects, and these are depression severity scores before and after an earthquake. So this was before the earthquake, and then 3, 6, 9, and 12 weeks afterwards. Okay, so you can't just use a matched pairs t-test to examine this because you got more than 2 samples, so you'll need to use an ANOVA. But since these are related, you wouldn't want to take, just this week 12 column and shuffle all these up, because then you wouldn't know which number goes with which subject anymore. Okay, so this is these are dependent samples; they're not independent; they're related, and so we'll want to use the repeated measures ANOVA. Okay. Now, these are just some means here for each subject. Depression score for subject 1 over the course of all these weeks is 6.6. Now for number 19, it's 11.8. And then you also have means for the week. For week 0 across all 25 subjects, 8.68. And you can see they get higher. And then this right here is the grand mean. This is the mean of all of these numbers, not including these subject numbers. That's just a nominal variable, but across all of these. Okay, so this is what the those means for each week look like over time. It's always a good idea to plot your data first, and this is you can see there's this trend that it's increasing after the earthquake and continues to stay pretty high. So for this type of ANOVA, the null hypothesis would be all of the means are equal, and the alternative would be all of the means are not equal. At least one mean is different from another one. Okay, so this is what's kind of going on under the hood when you run the calculation, and I don't expect you to know all of this in depth, but these are some things that we've encountered in other ANOVAs where you're taking the sum of squared differences from the grand mean. Okay, so you've got, sorry, that's pretty hard to read the subscript, but this is sum of squares total, sum of squares of the subjects, sum of squares of the weeks, and then sum of squared of sum of squares of the error. Okay, and you can see the numbers here recapitulated. For subjects, you've got let's see, 8.68. This you'd have like 6.8 here, 17.4, all the way, and this is multiplied by a factor by the number of groups you've got, and here by the number of subjects. But ultimately, you end up with these sums of the squared differences from the grand mean. So the grand mean is 10.448. I'll show you that one more time. So 10.448. So it's the sum of squares are the summed distances, basically, of each of these points from the mean across different dimensions. And then the sum of squares for the error is just a subtraction of the total minus the subjects minus the weeks. So just the source of variability that can't be attributed to any of these other ones, whatever is kind of left over. Okay, this is the type of output that you're going to see in Excel. Okay, so there is really only one effect that you're going to be looking at here that's of interest, and it's the only one that that shows up here. You'll see it sometimes in other in the Excel output, but there's just this one F statistic for the effect of the weeks. Okay, so basically that if this is significant, then these 5 means there's at least one that's different from another one. Okay, you can reject the null hypothesis because this p-value is low and this F statistic is sufficiently high. There are actually, as I mentioned, there are actually 2 independent variables going on here. The one independent variable is week, and then the other one is actually the subject. Okay, so you can see that there is a sum of squares associated with this other independent variable. So this would kind of be like a main effect of subject, but that's not really of interest. It's kind of a given that your subjects are going to differ from one another. They're not all going to be exactly the same, so we don't even really compute this because we don't have the right kind of denominator to compute this, to compute the F statistic. And the error, this is actually an interaction, but we're not really interested in this interaction either in this case. We're really just focused on the effective weeks. Like I mentioned, it's kind of more like a one-way ANOVA, except this error term here, or the variability associated with subjects, which is used to calculate this error term, which is used to calculate this, basically it just allows us to take into account the variability between subjects because we have related data. Okay, so acknowledging the fact that these subjects, even at baseline, even before any earthquake happens, even before there's any differences across weeks, they're going to be different from each other in terms of their depression severity. So we can account for that using this type of ANOVA instead of the one-way ANOVA. Okay, I will do a separate video showing how to do this in Excel, and I'll also illustrate doing just the one-way ANOVA that we've done before, just to show if we don't take into account that variability, then it gives us a quite different result. So I will sign off here and do that.